welcome to my talk on self-healing Kubernetes. Today we're going to talk a little bit about how Kubernetes as a distributed system can fail and how we can deploy the system in a way that we can mitigate these failures from the very beginning, so in the deployment model already. Can everyone see if I stand here? Like, is that all right? Cool. All right. Perfect. Who am I? I'm Max. I'm a software engineer at previously CoreOS, now Red Hat. I was working on the tectonic, on the distribution of Kubernetes by CoreOS. You can think of it as Ubuntu for the GNU Linux ecosystem. Tectonic is for the Kubernetes ecosystem. So here I was working mostly with the test infrastructure, bringing up Kubernetes clusters, doing that in an automated fashion, keeping up with our developers. So I've seen many Kubernetes clusters fail, and this is a lot of experience from my side, how I slowly explored the space of Kubernetes and how we can deploy this in a way that it doesn't fail anymore. Nowadays, you might know me from Prometheus. I'm one of the Prometheus upstream developers, mostly involved with Alert Manager, but also with the entire integration with Prometheus and Kubernetes itself. Okay, cool. We're a lot of people, so I'll probably not cover any question that comes up all the time or anytime. But for sure, feel free to ask them afterwards, or if there's something urgent in between, I can also do that. Reach out to me if you want some Prometheus news. Follow me on Twitter, and shoot me an email if you want. I'm also sticking around after this a little bit. Okay, cool. Let's start. So we want to deploy this new system called Kubernetes. Not entirely new anymore, but still, it's a complex system. It's a distributed system. And in general, it's software. So for sure, it's going to fail. No question around that. The only question is, when is it going to fail? And there are different ways how to cope with this failure. And I would phrase it as prepare for failure. We could either sit around and just act whenever something happened. We can have an amazing observability pipeline that will tell us before something happens, so we have enough time to just fix it. Or we really learn what the system is and how it works, and look at failures beforehand, and maybe even make certain failures impossible or easy to mitigate, or even automated to mitigate. So this is really what I want to cover in this talk. How can Kubernetes fail, and how can we mitigate it in some way? Okay, cool. As example failures, what can we think of? We can go insane, right? The world can go down, nodes can go down, the internet can go down, but we'll focus on a couple of areas. And that would really right now be the API server, or in general, the control plane components dying. Dying could be they are oomed by the operating system, or they simply lose network connection, or a node goes down, and all of these scenarios. So that's what we're going to focus on today. In addition, like, what if our entire control plane node restarts? Like, what is going to happen with our production applications? Okay. So before we can really mitigate anything, I first want to introduce a way on how to deploy a Kubernetes cluster, so we don't even have to cope with this, and hopefully this happening in an autonomous fashion, the entire recovery. And here I want to introduce self-driving Kubernetes, or self-hosted Kubernetes. You might have seen this GIF. I downloaded the slides as a PDF, so it's not that amazing anymore. But still, you probably heard of this idea before, and many of people have talked about it. It's not rocket science. It's not something entirely new, but the perspective to it is definitely worth talking about. I think Sergis, one of my colleagues, talked about it last year at a meetup here in Hamburg. And for example, I gave a similar talk at All Systems Go last year as well. So the idea of self-driving is we run Kubernetes in itself. Now we have a total chicken and egg problem here. It's a recursive problem, but like, how would that work? Let's go into that first. And you also see that in different areas. For example, in compilers, you see certain languages compiling itself in the end. So the idea of self-driving Kubernetes here, how do I run all the control plane components in Kubernetes itself, on itself, by itself, however you want to call it. So first I'll go into how to achieve that, and then how we can mitigate stuff for that. So let's first of all assume we have a kubelet running. With assuming that we have a kubelet running, I also assume we have a node running underneath, like a Linux operating system, and on that we start with systemd a kubelet somehow. We can go on different stages of going self-hosted, so we could, I don't know, self-host an operating system, but that would be a bit crazy, and I'm definitely not going to cover that. But instead, we're going to self-host anything from the kubelet up. So I would say this as a prerequisite. We have the kubelet, we start with systemd. Systemd is going to take care of it. Once we have that kubelet, a kubelet has a really nice, simple feature. The kubelet actually doesn't need control plane components to start pods, which is a very nice feature for bootstrapping something. And that would be, you simply have to put pod manifests into a certain folder on your node, and the kubelet watches that folder and starts pods according to that. So what we're going to do first is we're going to start a bootstrapping cluster, a bootstrapping Kubernetes cluster. These components here, the etcd, the API server, and the scheduler, and so on, these are really ephemeral. We're going to throw them away at the end, but we really just need them for the bootstrapping process right now. So once we have these started, we'll put them in that folder. Kubelet will start them up with the use of Docker or whatever container engine you have running underneath. And once we have that, we have an ephemeral Kubernetes cluster, but we have a Kubernetes cluster in this moment. We can start up whatever we want. You definitely don't want to start your production applications on this, but we can definitely start other Kubernetes control plane components. So what we're going to do here now is start the actual Kubernetes components on this. And that would be our real etcd, our real API server, our real scheduler, and so on. These we're hopefully not going to go throw away, but in the end keep through the entire bootstrapping phase. Now you might be asking, okay, 2 API servers, that sounds a bit dangerous. 2 schedulers for sure sounds very dangerous. What we do here right now is these self-hosted components would simply idle around right now. They wouldn't do anything. They would just wait there. We do simple leader election via Kubernetes, and thereby can set them on pause for now and not have them do anything. Then once we have this, we can transition the state from our bootstrapping etcd over to our self-hosted etcd. This way we make the self-hosted cluster aware of itself. So it knows that it itself is a pod on that node in a Kubernetes cluster. And last step would be simply killing the bootstrapping components. So simply removing the manifests out of that folder. That would remove the ones from the kubelet. The kubelet will clean up. And at this point, the self-hosted API server notices, oh, there's no other API server around, becomes the leader, and takes over. And at this point, you have a fully self-hosted Kubernetes cluster. OK. Cool. Any questions for that? Cool. Perfect. Now, I mentioned at the beginning, we have the kubelet as a prerequisite. I hope you can see that a little bit. It's kubelet up here. It's definitely very bright. And we can go crazy on this. What we at CoreOS previously been doing is saying self-hosting etcd is really just an experimental feature, and self-hosting everything underneath this. So running the API server in its own Kubernetes cluster and so on. You can go crazy. Again, you can self-host the kubelet, but that is very difficult to maintain. So whoever has questions around this can reach out to me later, but I think that that's a bit too much for this talk. Okay, self-hosting DNS, that's really not a big deal. You deploy the pod on your Kubernetes cluster and other pods talk to it. So that's not very difficult, but API server, of course, as you've seen in the beginning, needs a bit of a process here. Cool, all right. Now, next step is, why would I do this? I said we're going to mitigate all kinds of failure scenarios. First of all, there's a bunch of other stuff that helps us here. First of all, deployment consistency. You already know how you deploy your applications on Kubernetes. Why not deploy your Kubernetes the same way? And thereby, you have the same idea, the same learnings that you need here. You have easy introspection. Your Kubernetes cluster already helps you to introspect your application. You can look at logs. You can look at the status. You have health checking on all of that. now you have the same for your control plane components. So you can look at the logs of the API server. Kubernetes would restart them automatically if they fail, and the whole package. Then next up, what CoreOS was all about is cluster upgrades. So what we already showed with CoreOS Container Linux is auto-updating an operating system, and now the idea is to auto-update a Kubernetes system, and that is very easy if you self-host your stuff, because updating the API server is simply deploying a new API server or bumping the image version and then killing the old one, and then the new one would take over. And last one, we want to go high available here. We don't want our Kubernetes clusters to fail. So easy high availability configuration. For example, I can simply scale my control plane components. It's simply like kubectl scale in this case. So easily scaling up, scaling down, having high availability across multiple nodes. Okay, all right. So let's look at some failure scenarios that I introduced at the beginning for a cluster that is a simple multi-node, multi-master Kubernetes cluster. So on this Kubernetes cluster, we have multiple API servers. The API server could just be a proxy around etcd, right? But it does have state in terms of caches. So there are some problems running multi-master, but so far we haven't had enough problems to not use this way. Next one would be the scheduler. We would use Kubernetes leader election feature for this. So you really only have one scheduler running at a time, and you really only want to have one scheduler running at a time. The other ones would just idle around. And then in addition, we would do the same with the controller manager and so on. Taints and tolerations, of course, help us to spread this out across multiple nodes. So we don't have all our controller managers on one node. And maybe even spread this out over across availability zones and so on. Okay, cool. So we have our Kubernetes cluster set, self-hosted, multi-master. What happens if different things fail? So first of all, what happens if the API server in this case dies? Like if a single API server dies, in any multi-master setup, you hopefully just simply don't care, right? Like it doesn't matter, another one would just simply, all the traffic would be rerouted to the other ones, and the other ones would answer all the questions. So you really don't need to wake anyone up or anything. In a self-hosted way, this would also mean that Kubernetes itself is aware of that API server dying, and simply by doing all its health checking features, restarting another one on a different node. So that means you could even go, like in a 3-master node cluster, you could in a single night, have 3 master failures, but still have your Kubernetes cluster running as long as there's enough time in between. In addition, you probably want your alerting pipeline to alert you on this, not waking anyone up, but for sure, like, I don't know, creating a Jira ticket or something, because like your API server should really not be ooming on a regular basis. But still, in a self-hosted manner, you don't need to take any actions right away. Same thing with the schedulers and controller managers. We have the Kubernetes leader election feature. One scheduler, let's say, gets oomed or something. Another one would be failed over to and simply elected a leader in this case. Cool. All right. Now, multi-master is a bit boring. Not in terms of running your production deployments are probably, hopefully boring. But for this conference, it's a bit boring. So I thought, why not go single master here? So having all our control plane components on that single master. That means scheduler, API server, controller manager, and so on, all the critical components. And now what happens if something gets killed here? So for example, what happens if the only API server in this setup dies? Now, you might be saying, okay, then Kubernetes is simply going to start a new API server. But the kubelet needs to talk to an API server in order to start anything. Thereby, it doesn't have an API server to talk to. Thereby, nothing is going to happen. You simply have a dead cluster at this moment. So we had the same problem, and people developing Bootkube developed the checkpointer. And checkpointer is a very, very simple little thing on a node. You annotate your pods, like your very important control plane pods, with checkpointer annotation. And what the checkpointer is going to do is simply, like, periodically take the API server manifest and checkpoint it to disk, simply saving it there. Now, if the API server dies, the checkpointer is going to notice this and start a bootstrapping API server, simply to have something around. Yeah, right now you only need help. So it starts it up via the usual case. It just simply puts that manifest into the manifest folder of the kubelet. That then would start a bootstrapping API server. With that, you're again able to talk to etcd. So kubelet is able to talk to etcd, talks to etcd and asks the etcd, what should I really schedule on me? And it's going to reply, a real API server, please. So it's going to start the real API server, and the checkpointer was simply going to clean up the old one, the bootstrapping one. And at this point, you're back to normal. You're back to a normal Kubernetes setup. Now, a single API server might be easy this way. What happens if a single master reboots? This is not only a question of failure, but in addition, a question of how do you, for example, update your single master Kubernetes cluster? Like at some point, you're going to have to reboot your operating system, and how do you do this in this case? So again, the checkpointer comes in very handy here. The flow would look like this. You reboot your machine, systemd would kick in, like when it starts, systemd kicks in, starts the kubelet. The kubelet also already starts the checkpointer over the given manifest folder. The checkpointer would kick in, notice, oh, there should be an API server, but there's really none. So it starts a temporary API server. That via that temporary API server, the kubelet can communicate to etcd or can communicate to that API server, notices that all kinds of control plane components are scheduled on itself, and then boots all of these. And all of a sudden, you're back to a full cluster. OK. All right, so that is pretty much mitigated as well. Now, these are the failures I wanted to cover today. And my big plan was to show a nice Kubernetes cluster that I can kill. Sadly, I'm going to China next week, so I shut down everything in my laptop, and I think I've had some networking problems. Anyways, I hope the Kubernetes cluster is booting in the background. I'm very curious. But if it's not, I can show that later to everyone. I would just finish my slides and then go to that at the final thing. OK, how could we, for future things, this is definitely not the only failure that Kubernetes can have. So different things that we looked into and that we're actually right now developing in a new idea of now that OpenShift and Tectonic is merged, how to bring up OpenTonic, OpenShift, however you want to call it. So one way is looking into self-hosting node bootstrap infrastructure. So all of this is core as container Linux underneath. So you would need to boot that somehow, need the configuration from somewhere, and why, for example, not the Kubernetes serving that configuration. Then in future failure talks, we could look into etcd, partial failures, that's for sure interesting. And then, for example, what about your pod networking? What if your flannel control node dies? You still have the Linux kernel underneath it, but you're definitely not going to have any new pods joining into your cluster. So all of this is future things here. Cool. All right, let me check if this came up. All right, I'm right now connecting to Matthias' cell phone because I simply can't get into the wireless here. Anyways, I don't feel comfortable doing that on stage right now. But I'm happy to show that later once it's fully booted. And what I wanted to show is I have a Kubernetes, I have a Tectonic cluster up on libvirt on my machine. Simple 4 machines, I think 1 etcd, 1 master node, and 2 worker nodes. And then I would have just simply rebooted the master machine and then showed you on the steps how systemd kicks in, how the kubelet kicks in, and so on. Maybe I can show this at the very end. I'll just hang around a little bit. Whoever's interested can see that. Yeah, later on. Cool. So last thing is all of this was 100% open source. So what I would really appreciate is if you play around with the entire stack, let it be Bootkube, let it be Kubernetes, let it be your observability pipeline with Prometheus or so on. File bug reports. And if you also want to work on open source and want to work on this stuff, we're currently hiring in Berlin multiple Prometheus roles, test engineering roles, and so on. So just feel free to reach out to me after that. Okay, all right, that was it. Thank you very much.